All right, good afternoon, everyone, and welcome to Berkeley Lab, our Berkeley Lab Science Series, Live Science. Today, we'll be talking about ClimateNet and atmospheric rivers. This is an opportunity to share great hobbies and also interactive research and innovative research with our research scientists here at Berkeley Lab, and sometimes with our friends who join us from around the Bay Area. We want to remind you that you can follow us on social media. So we've put up our Twitter handles for our K-12 team, LB&L Next. I am Faith Dukes, our manager of K-12 STEM education programming here at Lawrence Berkeley National Laboratory. Today, we will also have representatives from our Earth and Environmental Sciences area, as well as our National Energy Research Supercomputing Center, or NERSC, as it is put down there in our Twitter feed, in the Twitter handle, and then Berkeley Lab you can follow as well. I'm going to remind you about some things today. So if you haven't already, there is a worksheet that has been developed for this session. You can find it at k12education.lbl.gov, and you can see that also in our chat box. We will also have a Q&A session after the session is completed and our information is given, our presentation is finished for today. So please stick around for the last 10 or 15 minutes where you can ask questions of our presenters today. For those who do have questions, my colleague Jennifer Johnson, who is a Senior Research Associate at the Joint Genome Institute has joined us today, and she'll be watching our chat box. So hi, Jennifer, how are you doing today?
Hey, Faith, I'm good. How are you?
I'm doing good too. So thanks, Jennifer, for continuing to support us in this effort and for watching the chat box and stepping in when we have enough people who've asked questions to our presenters over the day. So we look forward to seeing you throughout the session.
Of course, I'll see you in a little bit.
All right. So I also want to put in that for those of you who are just joining, you may not know, but we are Lawrence Berkeley National Laboratory. We are one of 17 national laboratories that are funded by the Department of Energy, and we are all across the nation. We are all doing innovative research, interdisciplinary research here at Berkeley Lab, which is all unclassified, but each of those Department of Energy national laboratories have their own mission that they are completing. And so you can see on our map, we have an interactive map there is at symmetrymagazine.org, which talks about each and every national laboratory that you can find out about, and they all have their different offerings as well around K-12 education, as well as learning and speaking to the scientists that are available. So we are here in Berkeley, California, as I said. And here's a look from above. Usually when we are on site, this is where we're doing all of our work. And today we are focusing on one specific topic around science in the sky, or as we called it, science in the sky, atmospheric science. So a little bit of the background for today, we want to start with some words that you might hear. And don't worry, on that sheet that I told you to download, there is a definition for it, as well as our speakers today will also go through them. So artificial intelligence, atmospheric river, climate, climate change, vapor, and weather are some of the words you will hear. And speaking of climate and weather, my first question to you all in the chat box is, what's the difference between weather and climate? Can you all answer that for us and see what people say? We want to hear what you have to say. While you're answering in the chat box, I want to bring on my friend, Dee. So, Dee, can you help us out with this question? And can you introduce yourself to us before we get started with answering that question?
Yeah, of course. Hi, Faith. Hi, everyone. My name is Dee, and I'm actually the executive director of a program called Science at Cal. Science at Cal creates opportunities for scientists at UC Berkeley to celebrate science with the public. So we have things like science cafes and lectures and festivals and all types of things. And I hope that someday we'll meet you in person after COVID has ended, after this pandemic has been solved. But I wanted to make sure that you know that you can contact us on the web. I have my website up here, over email, and also we're on Facebook and Twitter too at Science at Cal. But what's really interesting about me is that while I do run Science at Cal, I'm also a climate scientist. And more specifically, I'm an atmospheric physicist. And what that means is that I learned a lot about how the physics of the atmosphere and how the climate of the Earth is changing. So back to the question, what does that even mean? To answer how the climate is changing, I'm going to think about weather and climate again. So Jennifer, what were some of the answers in the chat? Can you join me and give me some of those answers? What were they?
Hey, Dee. So yeah, we have a couple people chiming in that weather is in terms of weather right now, and climate is over a period of time. Weather is what's happening at a given time. Climate is a pattern. And weather is happening right now. Climate is happening over a long period of time and happening in the atmosphere.
Wow, that was a lot of really great and all accurate answers. So I'm so glad you guys are setting us on the right path. So yes, climate and weather are actually very, very much related, but it's helpful to understand how they're different also and how they're similar by using the analogy of our wardrobe. So if we think about our wardrobe, I'm going to ask Faith. Faith, what did you wear in Oakland at the farmer's market this weekend?
So I wore a dress with a sweater over it, but then I ended up getting a shop, and so it was pretty warm, and I didn't have the sweater on for most of the day. But as the sun was setting, I decided to put the sweater back on. So originally with the dress on, I had the sweater on, and then I took it off because it was way too hot, and then I had to put it back on because it got way too cold.
Okay, that's so typical Bay Area, right? That's how we all live right now and play in the Bay Area. So that's actually a really great example of weather. So the weather in Oakland was warm during the day and cool in the evening. So you had to pick your outfit on that day based on what the weather was. Now, I've lived in the Bay Area almost my entire life. So my closet is filled with mostly dresses and sweaters and jeans and of course an umbrella, right? But I've never actually owned a proper coat until I moved to the East Coast. I moved to Washington, D.C. a few years back, and all of a sudden I had to buy things like heavy wool coats and snow boots, and I actually had to buy a scarf that went around my entire face so that it could be protected from sub-freezing winter days. So in that case, my entire wardrobe can actually be thought of as the climate, right? The Bay Area has a mild climate, only requiring a closet full of light clothing. But like Washington, D.C., it has a more extreme climate. So you have to buy things like coats and scarves that wrap around your face for the really, really cold days as well. So, yeah, Faith.
Yeah, so you would say that weather is more day-to-day changes, like picking out what you're wearing for each day. And then climate is what the weather is like over a year or a longer period of time, making up the entire wardrobe's worth of clothing.
That's exactly right. So there actually is a tiny bit more to that, because what a lot of people were saying in the chat responses and what we just talked about was about time, right? Like a day to day versus an average pattern. So all of the responses in the chat box were focused on that bit of time, but there is something a little bit more to it. So to explain, I think it makes sense if I bring in a more formal definition of what weather and climate are. So weather is the state of the atmosphere, and we can think about not just temperature, right, but weather, what the pressure is like, if it's cloudy or not, if it's precipitating, meaning is it raining or is it snowing, is it windy, right? All of these things make up the weather at any given point in time, as a lot of people said, but also in space. Whereas climate, again, what a lot of people said, is an average pattern of weather over a longer period of time. And some say that that's actually should be considered a minimum of 30 years. So 30 years, 40 years, 50 years, right? So anything above 30-year average pattern within a particular region. So in that case, if I wanted to ask about weather, I might say, did it rain yesterday in Berkeley, or will it be cloudy in Albany tomorrow morning? But if I want to ask about the climate, I may say, is cloudiness increasing or decreasing in the entire Bay Area over 50 years? Or is California more or less rainy now compared to 100 years ago? So thinking about California and the Bay Area, bigger chunks of land, and also over 50 years versus 100 years.
Okay, so we got the summary all ready to go, and we'll be learning more and more as we go through the hour. But just to summarize, our first thing is that weather is like the rain yesterday in Berkeley and clouds tomorrow morning in Albany. Climate is the average rain over 100 years in California and an average cloudiness over the last 50 years in the Bay Area.
Yep, so longer periods of time and longer geographic areas. You got it. So people may have heard that the climate is changing. So go back to our clothing analogy, right? We might want to ask ourselves this question on the slide, right? How is our wardrobe changing if the climate is changing also? So is it more or less rainy in California now versus 100 years ago? Or is it more or less rainy in the Bay Area? So to answer these questions, we'll definitely decide what our wardrobe will look like, right? Is it cloudy? Is it raining? And that's going to decide what our entire wardrobe will look like. But now what I want to show you is actual data of the Earth's temperature. Look at this plot. Look at this is average temperature from 1880, excuse me, this is a temperature anomaly, which I'll tell you what that means in just a second. So not average temperature, but temperature anomaly. But the time range is between 1880 and about 2020, where we are now, right? And you'll see that this is an animated video. You can see that those plots of what the temperature is changing, right? So again, on the x-axis, we have the year, and on the y-axis, what we have is what we call temperature anomaly. And I'll tell you why climate scientists do this in just a second. But what we've done is we've taken all of the temperatures and we've averaged them. Then we've called that average 0. So anything that falls below that average looks like a negative number, and anything that falls above that average looks like a positive number. And what that does is it helps us see maybe the difference between 75 degrees and 76 degrees isn't that clear. But if we zoom in like this, then you can actually see, oh, that's not a difference between 75 degrees and 76 degrees. It's actually 1.3 degrees, right? You can see the changes more. It's a little bit more zoomed in. It's easier to understand what the overall change is. That's why we do this. So what's super interesting, should have asked you, what do you think is interesting about this plot? So what you see here is you see, first of all, that the line is going up and down and up and down and up and down, right? It kind of has a very jaggedy look to it. And what that says is that from year to year, the temperature could jump. It could be very high, it could be very low, right? That's why we don't want to think about climate in a really short time period. We don't want to think about the climate over 1 year or 2 years because it's so jaggedy, right? But if you take a step back and you look at the temperature changes over this entire, what is it, like 140 years, then what you see is you see a steady increase. If you squint a little bit and ignore all that jaggedness, you can see that line increasing and going up. So between 1880 and 2020, the temperature has changed about 1.5 degrees on average. You can see I drew that red arrow so that you'll be able to see that even more clearly at the end of this. Between 1960 and 2020, there's been a huge increase, right? So I hope you all can see that at home. But this kind of brings me to this question, like, who even cares, right? So I want to ask you at home, why does a couple of degrees even matter? Like 1.5 degrees, why does that matter? So why don't you go ahead and answer in the chat box why 1.5 degrees might matter? I'll give you a minute or two, and then I'll ask that Jennifer pop back in and help share with everyone what those answers might be.
Okay, so the answers are starting to come in,
Okay.
and we're getting things like a big change over time. It can make a big difference because it affects wind, rain, pressure, and
Yeah.
sea level rises.
Yes. Okay. So we have some super smart people watching this webinar right now. You're getting all the right answers. I love it. So as you were right last time, it's very true. Temperature changes a bunch of different things. I'll give you examples of what those things could be. And I also, the sea level rise, that's very important, right? And we know that that's important. We live in the Bay Area and we live next to the water. I mean, it's important for the entire globe as well, but we feel it a lot. We recognize it a lot, right? And we talk about it a lot because we live right next to water. So that's great. Even though a few degrees, it doesn't seem like a lot, especially when you're averaging temperatures over many years. A warmer average temperature means actually more extreme days. So that's one thing that wasn't answered, but I just want to point that out. It means more extreme days of heat, and I'll show you. So my next plot, I'm going to walk you through this just like I walked you through the last one. So what this is a bell curve, and what this is a probability. So you'll see on the y-axis this time a probability, and on the x-axis is what the mid-afternoon temperature is. So that peak is at about 86 degrees. I know we're always thinking about Fahrenheit, but this is in Celsius. But the peak is at 86 degrees Fahrenheit or 30 degrees Celsius. And as we warm up, that entire bell curve is going to shift over to the right. So we're going to have, on average, more warmer days that are probably like 31 degrees, right? That bell curve is going to peak. That peak moves. Not only does that peak move 1 degree, 1.5 degree, where we're going to have on average hotter, these are summertime days, I should say. This is summer, mid-afternoon summer days. So this is the hottest temperature it is in the summertime averaged. I forgot to say that. So summertime temperatures are going to get 1.5 degrees hotter, but you'll see that there's this vertical line, and that vertical line lands on 34 degrees Celsius, which is at about 93 degrees. So if you think about the red area under the curve, that's the probability that we're going to have. What that 93 degrees signifies is it signifies extreme heat. So everything to the right of that are number of days or probability of days in the year that will have extreme heat. Now, if that entire curve moves over, the area under the curve, which is what that red is, it's going to increase. So you can see the area above the curve, or excuse me, below the curve, as the curve moves to the right, it becomes bigger. And what that means is we're going to have more extremely hot days. So it's not just that the temperature is increasing a little bit, but it's also that our extremely hot days, we're going to have more of those, which is dangerous. And also I'll tell you why in just, well, you'll see it here. The extremely hot days are dangerous because those are things that impact public health. So people may get sick more, they may end up in the hospital more, and they may actually end up dying more. Those extremely hot days are really bad for the public. There's lots of other things, right? There's increased wildfire threat, decreased snowpack, heavier rains, our rivers are going to be affected, and the list goes on. Oh, I shouldn't leave out, right? Sea level rise. Somebody mentioned sea level rise in the chat. So sea level rise, you'll see that there. Coastal flooding, ocean acidification, which also is something we talk a lot about. So it's not just extremely hot days, it's all of these other things. And the crazy things is that these things are happening across the world. So this next plot actually shows us that all of these crazy plots, let me see the next plot, which shows the globe, is going to, I know it's hard to see, it's kind of a lot of information coming at you all at once, but if you Google state of the climate, you can actually see this plot, and you'll see that every single country and continent all around the globe, there's going to be information about how climate change has caused an extreme event. Maybe that means that it was the world record in Asia for temperature that year, right? Or the Asian, not world record, but the record for highest temperature in Asia that year. or maybe it was the highest temperature for Arizona that year, or maybe there was an extreme weather event like a hurricane, or maybe there was lots of ice in Antarctica or the Arctic. So it's not just California, it's not just the United States. Climate change is affecting our entire globe, and we'll see how these extreme events change in plots like this. What's really cool is that you can see these plots for every year. So you can look up 2018, 2017, every year that we've been doing the state of the climate plots. So again, please look these up, and you'll see some really cool stuff.
Great, so thanks, Dee. So now we've got climate versus weather, and we have talking about the different, or the reasons why we should be concerned if we go up a degree or so in terms of the Earth's overall temperature. And so the summary of the effect of that degree increase is that we have extreme heat events, illness or death, wildfires, snowpacks, decrease in snowpacks, heavy rains, increase in river conditions, and probably rivers are drier or flooding, different lands, sea level rise, coastal flooding events, as well as an increase in ocean acidity. Do we have it all there? But I'm sure we're probably leaving out a few more things.
We're leaving out a few things, and I think we'll talk about that in a second too.
All right. So I'll let you continue on talking about the next thing. So, but let's get into that. We talked about extreme weather, but for the audience, what are some extreme weather phenomena that are happening here in California? Does anybody know, or have they experienced, or have you experienced any of those extreme weather conditions? And can you write them down in the chat box? Jennifer will, if you can help us out, I'll step out.
So I was just letting them come in. We have a couple: wildfire, drought, heat waves, heavy rain, hurricanes, really hot days, atmospheric rivers, droughts. We have really good participation today. Sonomi. Oh, that one's a hard one. I think that's all.
Yeah, these are all really good. Okay, you know what? I'm going to do everyone a favor, and I'm going to stop talking. I'm going to bring in a good friend of mine who's also a colleague of mine, and his name is Travis. He's a scientist at Lawrence Berkeley National Lab, but he's also a professor in the Department of Earth and Atmospheric Sciences at Indiana University in Bloomington, Indiana. So he's also an expert in California's changing climate. So I think it's more appropriate if he's more equipped to answer this than I am, because he's an expert in this subject. So Trav, you want to come on and join me?
Well, thanks, Dean. Hello, everybody. I'm actually not sure that I have much to do. I think in the chat box y'all stole my steam here. I mean, maybe I can take a step back and talk about this in terms of the weather that you get in California. I mean, so let's think about this. It's sunny, it's foggy, it's rainy. It's pretty much one of those three on any given day. It might be snowy if you live in the mountains. So these extremes are when you get too much of any of those. So you recognize we get some days that are just too hot. There's too much sun. We get drought when we have too much sun for way too long without any rain. We get wildfire a lot of times when we have those drought conditions along with really hot and windy conditions. And then of course we get floods. And this lower image I think is showing a flood associated maybe with storm surge, but we also get floods associated with rain events. And there's a particular type of weather event that I'm actually impressed that one of you, I think a guy in the chat box said atmospheric rivers. Most people that I talk to have not heard of atmospheric rivers, so I'd like to introduce them. But let me talk about this in terms of something that you're probably more familiar with first, which is, so Dee, do you remember a couple of years ago, this was February 2017, this particular image made really big news, the Oroville Dam spillway.
Yeah, I think that was everywhere at that point. Everyone was talking about it.
Yeah, so that was a big deal because there was so much rain over a fairly short period of time that they couldn't divert water away from the emergency spillway. It went over the emergency spillway, and you can see on this image what happened. It eroded a lot of land. Fortunately, there were no deaths from this, but was something like $1 billion worth of damage that is still being repaired from this. This was caused by a series of atmospheric rivers. So in order to give you a more concrete idea of what an atmospheric river is, let me actually show you one. So this image here actually shows the atmospheric river on that day, the day that caused the spillway incident at Lake Oroville. So what we're seeing here in this globe, the pink and orange areas show areas where there's a lot of water vapor in the atmosphere. That might mean there's clouds, but in a lot of areas, particularly in the tropics, it's just water in the air that you can't really see, but I think you kind of intuitively know that it's there. Like when we say, oh, it's really humid out today, or it's really muggy, that's water vapor in the air. There's lots of water vapor in the air. Or when it's really dry, like, you know, sometimes in the summer it gets so dry that like your skin's cracking. That means there's not much water vapor in the air. So the tropics have a lot of water vapor. That's where most of the water vapor in the planet in the atmosphere is. But sometimes we have these weather events where we get these long, narrow corridors of water vapor coming and hitting the coastline. And these are really important, actually. I'm hoping that dialogue like this gets us more into the public knowledge of an event type that's really important for California. It's important because pretty much all of the last major floods that we've had over the last 20 years in California have been atmospheric rivers. Most of our precipitation in California comes from atmospheric rivers. Just a handful of these falling each year brings most of the rainfall. And on the flip side of that, when we have droughts, it's usually because we're not getting many atmospheric rivers in a given year or over a span of years. So let me talk about this from a more formal definition, the American Meteorological Society definition of atmospheric rivers, which might make this a little more concrete. So they give this really nice definition. They're a long, narrow, transient corridor of strong horizontal water vapor transport. That's just a fancy way of saying that the wind is blowing a lot of really moist air from the tropics into the mid-latitudes, which are the latitudes that California sits at. And if we think about this in terms of things, you've probably heard of this. If you ever watched the Weather Channel or you watch the weather forecast on the local NBC News or something like that, you might hear the weather forecaster say, and we have a low pressure system coming out of the Gulf of Alaska, bringing a front along with it. Something like that. So atmospheric rivers are commonly associated with these low pressure systems that have fronts, meaning you've got cold air coming from the north, meeting warm air from the tropics, and where they meet, you get the air flowing from the southwest to the northeast in the direction that that arrow is pointing. And what that does is it basically points a fire hose of water vapor towards the coast. The reason we call these atmospheric rivers, by the way, is because the amount of water that is flowing in them in this fairly narrow area. I mean, it's maybe a couple hundred miles on the side relative to being several thousand miles long. The amount of water that's flowing in them is about as much as is flowing out of the mouth of the Amazon River or the Mississippi River at any given time. It's literally a river's worth of water flowing in one single weather event. So really important way to bring water to California. Now, we have to ask ourselves a question, why does the water vapor matter? I mean, we're talking about water that we can't necessarily see. How does this matter for rain? And to answer that, actually, I want to ask Dee, because Dee is a cloud physicist and she is an expert in this and way better equipped to answer this than I am.
Thanks. I like how we're just like punting to each other, right? That's a really good question because it's true. It's like there's all this water, we can't see it. It's just moving around the atmosphere. Who cares? Well, when it hits those mountains, what ends up happening is that air has nowhere else to go but up, right? It's moving around and it hits that surface and it's like, oh, I guess I better go up. And if you think about what happens to the temperature of the atmosphere as you go up, so maybe you're driving in a car and you're climbing up a mountain to go look at a view or to go hiking or something, you might notice it's colder higher up. Or if you've ever been in an airplane, or if you're ever going to be in an airplane, Go ahead and touch the window on the airplane, and you'll notice that though it's very, very cold outside. So what happens is that actually the temperature of the atmosphere decreases as you go up. So all of a sudden you have all of this really moist air, right? Air with a lot of water vapor in it, and it's getting pushed up, and it's getting pushed up into colder atmosphere. So it rapidly cools the air. And I actually wrote a recipe for a cloud is cooling air, which is what you would have when the air is forced up. And it's also water vapor. We're talking about air that's has so much water vapor in it. You add those two things together and you get a cloud. Clouds are made up of actually suspended droplets of liquid water. So what happens as you get cold, moist air, the water vapor inside actually condenses onto little particles, and you get droplets, liquid droplets. I know sometimes it's hard to think about a cloud is made up of liquid, but it is. It's instead of water vapor, we have liquid water, lots and lots and lots and lots of little drops of liquid water, but they're not big enough to ever come down, right? They kind of just stay aloft in the cloud. But if you want to make rain, all you have to do, this is a recipe, it's almost the same. It's actually lots of cooling air and lots of water vapor. So you're adding a ton of water, moist air into this already formed little liquid water droplets in the cloud. And what ends up happening is those liquid droplets grow and grow and grow, and they start running into each other, and they start running more and more and more, and all of a sudden they're huge and they fall out of the cloud as rain. So that's how you get a cloud, and you add even more moisture and more cold air, and then you're going to get even more bigger droplets until it rains. So that's what happens when you move moisture over a mountain, Travis.
Mm-hmm. And I mean, this is exactly why, yeah, that when that rain hits the mountain, it has nothing to do but rain out. Mm-hmm. So, yeah, I mean, you get that atmospheric river hitting the mountain, and that river turns into actual liquid water that falls on us. So, yeah, I guess let me just summarize atmospheric rivers real quick for you, just to recap what we've heard. So they're long, narrow corridors of water vapor that come from the tropics. There's not many of them. I didn't say this, but we only get maybe 20 in a given year. Sometimes we only get 5. But the few that come, they bring most of our rainfall. And they're also, so they're a benefit, but they're also a hazard because they also cause floods. So these are, if you take away anything about atmospheric rivers from this, I'm hoping this is what you'll take away. So I've been talking a lot about atmospheric rivers and stuff, but Dee, I think you started this conversation from another angle. You were talking about your wardrobe to begin with.
Yeah, actually, there was a question that came up on the chat, and I kind of want to answer that. So somebody asked, let me see, my 10-year-old wants to know why it's colder at higher altitudes if heat rises. And that's such a good question. It's such a great question. So I will answer this by, have you ever noticed that if you're laying out in the sun, that your body gets very, very warm, or anything laying out in the sun, maybe the asphalt or an apple, or it doesn't matter. It's laying out in the sun and it gets warm. That's actually what's happening to the earth. So the earth itself is absorbing the heat from the sun and it's warming up. So if you go higher up in the atmosphere, what ends up happening is you're getting farther and farther away from the source of the heat, which is really the earth. So that's a way to answer that question in a brief and quick explanation. But that's why you're just moving away from the source of heat in the atmosphere, which isn't the sun actually, right? Because you can feel warmer than the air around you, right? The heat is actually coming from the earth because the earth warms up. So that's why you get colder air as you move higher up into the atmosphere. So that's a really good question. Okay, so we talked a lot about changing climates, right? And I talked a lot about changing climates, and Travis talked a lot about atmospheric rivers, but actually I don't know, Travis, is climate change affecting atmospheric rivers?
I was afraid you'd ask that. And the thing is, I don't know. And it's actually fascinating, the reason that I don't know. And really, we have some idea, but there's a lot of work to do. And let me describe to you why by showing you an image here. So this image shows, so you're going to see, this is a satellite view of weather on the West Coast over a period of about 10 days. Each time it goes dark, that's nighttime, so the sun's gone away. Now, this is a satellite image where the satellite is taking a snapshot every 15 minutes. Now, imagine having to find and identify an atmospheric river in that satellite image. But let's think about this. If we're talking about climate change, and Dee said if we're talking about climate, we need to be thinking about 30 years or more. And if we're talking about climate change, we need to be thinking about even longer. So we've got a satellite image every 15 minutes. That means there's 4 of those per hour. There's 24 hours in a day, 365 days in a year times about 40 or 50 or more years. We're talking about something like 100,000 images. And then if there's like 10 or 20 atmospheric rivers that hit in a year, we're talking about counting millions of these. So if we want to ask, are there more or less atmospheric rivers as the climate gets warmer? We have to identify them. And that is a monumental challenge. It's what we call a big data problem. You have to sift through a lot of weather data in order to find essentially the needle in the haystack. The needle is the atmospheric river and the haystack is the global weather system. So this is why I'm really grateful to work with people at Berkeley Lab. And I'd like to actually take this moment to introduce my colleague, Dr. Karthik Kashinath, who is an expert in machine learning and artificial intelligence, which is really, in my mind, the way to solve this problem. I don't want to, nor can I actually count all these myself, but I'm thinking that Karthik has methods that can do this with the assistance of machines.
Thank you so much, Travis. That was a fascinating introduction to climate change and atmospheric rivers and extreme weather phenomena in California and elsewhere. And we're now facing this grand challenge that Travis just spelled out, which is how do we identify these extreme weather patterns in large amounts of data? So let me ask the question to you guys. Travis mentioned artificial intelligence, and I'm sure you're hearing about AI everywhere today. So a question to all of you is, what are some ways in which AI is helping us today? Can you answer in the chat box? Thank you. Okay, we're seeing a few coming in.
Yes, so we have vision systems in medicine and computing, speeding up data processing.
Awesome.
Vacuums. Technically reaching locations we physically cannot touch or reach.
To answer all questions, brilliant. Okay. Well, clearly, as we can see, AI is changing everything that we do today, especially in technology, but also in science. And I'd like to show you how AI can actually help with detecting weather and climate phenomena in data. So just to introduce what AI can do, here is an example on the top row of photos that you could get from the internet, photos that you might take of your pets. And in the bottom row are images from satellites or climate models that show the types of phenomena that Travis and Dee were talking about: atmospheric rivers, hurricanes, weather fronts, and various other things. So AI can do at least 4 important things that we care about. On the first column, we have, if I give you an image, can you tell me whether there's a cat or not in it? That's something that AI is really good at doing. We could pose the same question for weather and climate science and ask, if I give you a piece of data, can you tell me if there's a hurricane in it? The second would be a slightly harder question, which is, if there's a cat, can you tell me where it is in that image? That's the second column. And you could ask the same question, if there's a hurricane, can you tell me where it is in that data set? Now we can make that question a little more hard by saying, okay, there might be cats, dogs, and ducks in that photo. The parallel in climate science would be there are atmospheric rivers, hurricanes, other types of interesting weather patterns in our data. Can you identify all of those? And finally, the last column shows not just drawing boxes, but tell me precisely what the boundary is for the cat and for the dog and the duck. And the same for weather and climate data would be, tell me precisely what the boundaries are for a hurricane or an atmospheric river. So AI is perfectly suited, as someone said, vision systems. AI is very good at being able to identify patterns in data. And that's exactly why AI could be very useful for this task that Travis posed, which is how do we identify thousands or even millions of such patterns in large amounts of data, finding those needles in the haystack. So that's where we are bringing in AI into pattern recognition in climate science. But before that, I want to take a step back and ask, how do we actually get these AI systems to work? What are they? How are they built? What sort of computers do they work with? And how do we actually get all of this AI to do the challenging things that we want it to do? So here we have a slide that shows us what science can be done with supercomputers. As Faith mentioned at the start, NERSC is where I work, which is the National Energy Research Scientific Computing Center, which basically hosts the large supercomputers that are used by all of the Department of Energy computing labs, but also universities, academics across the globe. So why do we need supercomputers for science? Supercomputers are very helpful to understand things that are too big. So understanding things like the universe, the galaxies, stars, how they're changing, things that are too small, things like small particles in physics, like protons, neutrons, or microscopic organisms, cells, and so on in biology. Things that are very slowly changing, like how is the universe evolving over billions of years. Things that are extremely expensive, like the types of experiments that one needs to do in physics and chemistry and climate science and so on. Things that are very dangerous, like if I want to understand how wildfires are changing, I don't want to actually go start burning forests and see what they're doing. I could try to simulate that on a computer. And also for replacing or augmenting all types of experiments that we do in science, because we now have computational power. So scientific computing and supercomputers are really changing the way we do science, and Berkeley Lab is at the forefront of this type of research. And this photo here is of the large supercomputer that we have at NERSC. This is Cori, which is sort of the latest flagship computing facility that we have. And it has the power of over 100,000 laptops put together into one machine, in fact, much larger than that. And this is the sort of machine that can make very large numbers of calculations very quickly, and therefore we can ask really hard questions to these computers and get answers in a reasonable amount of time. Great, so coming back to how AI can be used for detecting weather patterns, I'm gonna show you just 2 snapshots before we actually get to sort of the most exciting part, which is the demo. What you're gonna see in the demo will resemble the slide that we're seeing here. We have developed a tool called Climate Contours here at Berkeley Lab, which is a tool that takes in climate data. It could be from climate models, it could be from satellites like the ones that Travis showed us. And we can ask the question of how do we actually identify these patterns? And so we get experts to use this tool and label different patterns. And what we're seeing here are in pink, red, and purple are the atmospheric rivers that Travis was talking about, these thin, long filaments that transport moisture from the tropics to the mid-latitudes. And then in blue, we see a hurricane, which is approaching Mexico. And we'll see more of these when we get to the tool. So these are really helpful examples because they draw very tight boundaries around the patterns, they're very precise, and they capture exactly what we're looking for. On the next slide, I'll show you some not so helpful examples just to contrast how we might use this tool. On the top left, you see a hurricane near Japan, but there's a boundary drawn in red, which is way too big because it not only captures the hurricane, but it has various other things around it, and it's not quite precise. That's not very helpful because you're sort of misguiding the artificial intelligence system by not telling it exactly what the hurricane is. You're including too many other things, so it can get confused. Now on the bottom right, we have this pink object, which includes a big atmospheric river that's approaching South America, but it also includes a lot of other things. So once again, there are many different events that are combined together, and it's not quite a precise boundary. So this, again, is not super helpful because this might end up confusing the artificial intelligence system. So now let's move on to the tool. The link is in the chat box. This is a live tool that's available online. Everyone can use it. So you can click on that link and it'll take you to the tool. I'll start doing the same on my screen, and I'll share my screen in just a moment. Awesome. So if you've had a moment to load the tool, you might see it on your own personal machines. If not, you can also just look at it here on the Zoom window. So here, again, to recap, is the tool. We've called it Climate Contours. I'm just going to walk you through some of the features of the tool. First of all, the data that you're seeing here comes from climate models. These are models that are developed by climate scientists like Travis and Dee. They basically encode all of the physics of the atmosphere and all of these complicated things going on in the ocean, ecosystems, etc., into these large computational models that they run on supercomputers like Cori that I showed you, to basically simulate the climate and simulate the atmosphere and ask questions like, how is the climate going to change over the next 100 years? So the data that we're seeing here is coming out of these climate models. This is one particular instant. So if you were to take a snapshot at a particular instant in time, this is what the atmosphere, the state of the atmosphere would look like. Now on the right are channels. These channels refer to different variables or different physical quantities that climate scientists and atmospheric scientists care about. So Dee and Travis were talking about water vapor. That's a very important physical variable that climate scientists care about because that says so much about the state of the atmosphere. And what we're seeing here on this particular image is actually the water vapor in the atmosphere. So in green are regions with large amounts of water vapor, and in dark blue are regions with low amounts of water vapor. So as you can see, in the tropics near the equator, there's a lot of water. And as you move towards the poles, there's less water in the atmosphere. Now, what we also see here, if you remember from the satellite image that Travis showed of February 2017, is this really interesting large atmospheric river that's going all the way from the tropics towards the west coast of North America. Now, atmospheric scientists also like to look at various other quantities before they can be sure that a particular event is an atmospheric river or a hurricane or a weather front or a heat wave or a cold wave or a polar vortex or what have you. So one of the other things that atmospheric scientists care about is what is called integrated vapor transport, which is the combination of water vapor and wind. And what that says is where large amounts of moisture or water vapor are moving at a high speed and the direction in which it's moving. And that is actually the perfect variable to characterize an atmospheric river. So what you see here is this very bright region, this large, long atmospheric river, which is showing up in this particular variable because it's a large amount of moisture that's also moving at a high speed towards the northwest coast of the US.
One might actually say that that's a long, narrow corridor of high horizontal water vapor transport.
Perfect, thank you. That's the precise definition of an atmospheric river. So let's begin with using the tool. I'll show you some of the other variables in a moment, but since we have this large atmospheric river right in front of us, I'm very excited to actually label it. So on the top left here, you see the zoom in and zoom out buttons. That's just to get a closer view or to zoom out. And then the polygon tool, which is the tool that we're going to be using, helps us draw a polygon around this event. So what we're trying to do here is label the pattern precisely as possible so that we can then give it to the artificial intelligence system, and then it can start to learn what these patterns look like. So all you have to do is just click. Each time you click your button, your mouse, it drops a new vertex of the polygon. So you can basically track the boundary of this atmospheric river by closely following it and just clicking along the boundary. As you can see, I'm being very careful and I'm going precisely along the boundary of the atmospheric river. It kind of swings around near Alaska, so I'm also trying to capture that. And then at some point it starts to dissipate, so I'm going to stop right there and then follow it back around on the other side, going all the way through. And as you can see, I've already done about 20 or so clicks. You can do as many clicks as you like. The more the better, to be able to get a very clear tight boundary. And finally, when you reach this first point where you started, this box pops up, which asks you the question, what type of event is this? So the default is atmospheric river. I'm going to stick with that. The other option is a tropical cyclone. We'll get to that in a moment. So let's stick with atmospheric river. The confidence level, I'm going to say, is high because this is a very clear atmospheric river. It's large, it's well-formed, and I'm sure that it's an atmospheric river. And now I can say done because I'm happy with this. So now here in red is this big atmospheric river. Sorry, go ahead.
Can I ask a question?
Of
Yours
course.
says May 25th, 2003, but mine, my screen says January 18th, 2007. So what's the difference between your screen and my screen right now?
Great question. Thank you for asking. So what we see here on the top right is just a snapshot pulled out of a climate simulation. And these climate simulations are run for tens of years, sometimes hundreds of years. Now, the tool is designed so that we can get as many people as possible to label as many events as possible. So each time you start the tool, it randomly picks a new image from that large data set. So every person that uses the tool is likely to get a different image, and that way we maximize the number of patterns that we get labeled. So that's why everyone gets a different date. And there's a small chance that two people might get the same date, but we're trying to get as many people to label as many dates as possible. All right, so that was an atmospheric river, and that's been labeled. Now, since the other interesting event that this tool is designed to capture is a hurricane, I'm going to show you an example of a hurricane. Now, you might ask the question, oh, there's lots of other interesting patterns here on the globe as well. And that is indeed true. We have many other atmospheric rivers here in the southern hemisphere. There's interesting phenomena going on here in the Atlantic and probably here near China and so on. But just to refresh and get a new image, I'm going to hit the next button here, which you can also do. And by the way, if I know this is a very quick demo, but if you're interested in understanding more about how the tool works and exactly what these events are and what are the right ways to label them, you can click on this help page here, the question mark, and it'll take you to a full description of how to label these events. All right, so I clicked on the next image here, and now I see, of course, I've got a new image. This is, again, the water vapor field. As you can see, there's different types of patterns here. There's, of course, atmospheric rivers and hurricanes, but there's lots of other things going on. Now, let me toggle through the other variables. I told you that integrated vapor transport was super helpful for atmospheric rivers. Now, what about hurricanes? Hurricanes, as some of you are probably well aware, are these large spinning systems that transport large amounts of moisture, but also have strong winds, can cause huge destruction. We've heard about hurricanes on the East Coast, Sandy, Katrina, and so on. They're also affecting Asia and Japan and elsewhere. Hurricanes happen throughout the globe. So another important pattern that we'd like to label in these data sets are hurricanes. Now, I mentioned low pressure associated with hurricanes, and we have pressure at sea level as one of the variables. So let's click on that. What do we see here? We see off the coast of Japan is this dark blue area, which is a low pressure area. And off the coast of Mexico, we see another slightly less strong, but still nevertheless a low pressure region. Now let's look at the vapor transport variable. What do we see here? We see a very strong yellow dot here off the coast of Mexico. That's signaling a lot of vapor being transported, likely within a hurricane. Now, winds are probably the best way to identify hurricanes. So let's see what the winds are doing. As you can see here, there's these large arrow marks that are spinning, and in fact, they're spinning counterclockwise. And off the coast of Japan as well, we see the spinning structure. So I think there are at least two cyclones in this. I'm not going to call this one a hurricane, the one off the coast of Japan, because that is further away from the tropics, and it might be an extratropical cyclone. We won't get into that. But basically, there are these large spinning events.
And if you don't mind me jumping in here, if you could show the pressure field again, it's actually a really nice illustration of the low pressure system that we talked about that forms off to the northwest of an atmospheric river. So that is likely the mid-latitude cyclone that's associated with an atmospheric river. And I believe it was Robert asked a question. Keep this in mind. This bears on the question that you asked that we'll address later on in the Q&A.
Perfect. Thank you, Travis. All right, so let's label this hurricane off the coast of Mexico, because we know that that's got low pressure, it's got lots of moisture. You can see that sort of classic spinning structure there. I'm going to zoom in a bit so we can see that event a little more closely. And now let's start labeling it. I'm going to just start right there and go around. As you can see, there's these sort of bands, what they call the spiral bands associated with the hurricane. I'm going to try to capture that as well. And then sort of close off like that. Now, is that an atmospheric river? No, it's not. It's a tropical cyclone, also known as hurricanes in the Atlantic and typhoons in the Pacific. I'm fairly confident, so I'll say hi, and then I'll say done. So now I've labeled a tropical cyclone. So we've seen examples of tropical cyclones and atmospheric rivers in these data sets. And since you have access to the tool and it's live, all of you can go ahead and label as many events as you like and ask me any questions. And I might pause for a moment just to see if there are any questions from our audience.
No questions so far, but I'm sure we'll have a few more when we finish up. And I know we have one more slide to share.
Yes. Thank you. And apologies about the train noise in the background, but I'll try to speak over it. So since we're almost at the hour, let me sort of tie this all back together and explain what exactly AI can offer for us here. So we see on the left are human experts that are providing labels that feed into the ClimateNet data set, which is the large data set that has all of these expert labels. Now I told you about the AI model needing expert labels to sort of teach the AI model exactly what these events look like. So that ClimateNet data set goes into training the AI model. The bubble that we have here represents the unified AI model, which can capture atmospheric rivers, hurricanes, various other patterns. And once this AI model is trained sufficiently well, we can then use it on all types of new climate data coming from satellites, from observations, from other climate models, etc., to detect all of these interesting events, hurricanes, atmospheric rivers, weather fronts, and go back to basically what Travis posed as the challenging question, which is where are all of these interesting weather phenomena in this large amount of data? So once we do this, we've been able to identify all of these events, and we can give those results back to the climate scientist, to Travis and Dee, and they can start to ask really interesting questions about how extreme weather is changing in a warming world. All right, thank you.
Thanks, Karthik and Travis and Dee for joining us today. And that was a wonderful presentation and lots of information to take in. And hopefully many of you will be helping us out by actually using the ClimateNet tool in order to help our scientists identify extreme weather events and make sure that our AI systems can get better at detecting climate. So I'm going to have everyone turn on their videos again so we can see them. And I know Dee has to leave soon, but if we have any questions for her before she jumps off in, we had a really great question in the box that Travis alluded to. So we want to make sure we get to that one as well. And then we have a few more. So anyone who has any questions, we're going to stay on for another 10 to 15 minutes or so and get those questions answered before we end the session for today. So let's start off. And Jennifer, if you remember that question, or Travis, if you remember that question that was asked, we'll go back to that one to start off.
Yeah, I'm scrolling. Jennifer, do you have it up already?
Yeah, it's, so the listener believes that there are two major sources of winter participation in California, one being an atmospheric river, and often described as originating near Hawaii, and two, lows that drop directly out of the Gulf of Alaska, and that drop down along the west coast and turn in east either day over Oregon or California and produce rain. Is this correct? And what are the relative contributions to total seasonal rainfall?
Oh man, we have a scientist in training here. I think we
definitely do.
Yeah, I misattributed this, Patrick. Thank you for that question. And it's a fantastically detailed question and right at the heart of actually an active area of science and research that's going on right now. So you're correct to observe that atmospheric river is a term that has only originated somewhat recently. It first started being used in the late 90s when people started looking at satellite data more systematically than they had for the past 10 or 15 years, and realizing that a lot of the water that goes from the tropics towards the poles, most of it is actually happening in these long filamentary structures that are called atmospheric rivers. So the whole field sort of launched in the late 90s. So your observation of that, when you watch the Weather Channel or whatever, and they talk about a low that drops out of the Gulf of Alaska, that is exactly the sort of condition that can lead to an atmospheric river. So there are two separate types of weather patterns that you're correct in identifying. So Karthik named the thing as a mid-latitude cyclone. It's a fancy way of saying a low pressure system. These do generate rainfall, but they don't generate as much if they don't have a lot of water with them. So when a mid-latitude cyclone is able to capture a lot of tropical water, that, as Grace correctly said, the low pressure effectively draws that water vapor up into the mid-latitude cyclone, and that causes the atmospheric river. So one way of thinking about it is an atmospheric river is a mid-latitude cyclone that has picked up that tropical water. Now, the reason I said that this is an interesting debate in science is not everybody agrees with how I just described that. I'm actually not sure I agree with how I just described that. It's possible that atmospheric rivers have a life of their own, independent of these mid-latitude cyclones. Karthik had the first example. He showed that really long atmospheric river going from across the whole entire Pacific. You could, at least my eye was able to pick out that actually went across two separate cyclones. So they have sort of a life of their own. It's to me, really fascinating field. But the last part of your question that you asked, how much rain? Depends actually on how you identify them. And my colleagues and I actually just put out a paper last year sort of synthesizing the knowledge, and it looks like it's the numbers anywhere between about 30 and 80% depending on A, how you count them, and B, where you're at in California. More of the atmospheric river rainfall comes in the mountains because of what Dee described with the orographic uplift of the air. So that is probably way more thorough of an answer than you wanted, Patrick.
Thanks, Travis. I was going to say, Dee, do you have anything to offer before you have to leave us for today?
No, everyone's been really great at asking questions and responding to our questions. So I just want to thank everyone for being so active, and hopefully if we do more, we will get similarly active participation. So thank you everyone for being here, but I have to run.
Cool.
Thanks, Dee. So I'm going to ask, we have one more question. How can we help scientists and computers improve the detection of extreme weather events? We kind of went over that a little bit, but I'll let you guys, especially Karthik, answer that a little more definitively.
Sure, thank you. Yeah, that's a great question, and that's sort of central to all of what we've been talking about today. And that tool that we worked with is actually exactly designed to answer this question, which is, how can scientists help with improving the detection of extreme weather events? So maybe just to break that question down a bit, given that we're using artificial intelligence to detect these events, and as we said, AI is perfectly positioned to do this sort of thing, what AI systems need is a large amount of training data It is basically data from which the system can learn what these patterns look like and to identify them correctly in new data sets. So what can scientists do? Scientists can help by contributing labels to the ClimateNet dataset that was just described. So what we did in the last 15 minutes or so was to label these atmospheric rivers and hurricanes. Now, all of those labels get saved in a large database called the ClimateNet database, which is then used to train the AI system. And that's exactly what we've been doing with collaborators like Travis and others at the National Center for Atmospheric Research and elsewhere, having these large labeling campaigns where we have lots of scientists sit together, we give them pizza and coffee, and they're on their computers labeling atmospheric rivers and labeling hurricanes and lots of other exciting weather events. And in 2.5 hours time, we get thousands of labels. Now, each time we have one of those campaigns, we get thousands of labels, and very quickly we have, tens of thousands of labels, and that can start to help build this database to train AI systems. Of course, Patrick asked the hardest questions, which is what about mislabeling? That's a great question. So we have to design these tools in such a way that the not so helpful labels are filtered out. Now, that's not the easiest task. There are some ways of automating it where we have this sort of gold standard database, which is the leading experts in the field label maybe a few hundred images that we call atmospheric rivers, a few hundred images that we call hurricanes, and then we compare each new label against these existing gold standard labels to say, okay, you're very close to what the experts think are atmospheric rivers, so we're gonna say, yes, this is a reasonable atmospheric river label. Or you're too far away from this, so we think that this might not be quite right. So that's one way to do it. Now, the slightly more laborious, but perhaps foolproof way to do it is to actually edit, or not quite edit, but to actually review every single label after it's been labeled using, graduate students, postdocs, other scientists to sort of look at it and say, okay, I think that these are all good labels and we can proceed. Now, obviously, we don't want to change the labels too much because we're trying to capture the diversity of the ways in which scientists think about these phenomena. And as Travis said, depending on how you identify these events, you might have a large range of different results. So we don't want to sort of normalize all of that into one particular way of thinking. So we want to sort of capture all of the different ways in which atmospheric rivers are defined by different scientists.
Awesome, but the take home is we do want people to be careful with their labeling and help us out as much as they can by being as precise as they can and probably using that help tool that's on the website before they get started, because as we all like to think, our AI is only as smart as the users or the input. So the people who are using it and designing it can make our AI either smart or not so smart in terms of detection. That's very good for us to remember. Any more questions before we end today? Anyone have a last minute question that they want to put in? I'll give a second. All right. And if not, I'm going to say thank you to our panelists here today, Travis and Karthik, and as well as Dee in her absence, and Jennifer for joining me as well every time we do one of these. Happy to have you, happy to have everybody that joined us today. As we continue, we'll have one of these in August. We haven't announced the exact date yet, but we'll make sure we post it as well. We will actually have a seminar series next week, Monday through Thursday, all about STEM careers, and we'll be posting that on Eventbrite as well as on our website. We'll probably send out an email to everybody who signed up and registered for this one, so you guys will all hear about that and hear from more Department of Energy National Laboratory scientists and researchers here that are talking about their careers in STEM. So thank you for joining us, and have a great weekend, everybody.
Thank you.
Bye.
Oh, this has been fun.
Bye.
Thank you all.